All right, welcome back. So we just finished up problem example A here. And remember, what we were trying to do was we were trying to decide um, what x was in this situation. And remember, x in this picture is just the side length of a triangle. I'll kind of highlight that triangle because it got messy. It's just the side length of a triangle. And remember, when this side or this line just hits our circle one time, like this purple one does, we call that a tangent line. And remember, we said things are only tangent if they meet at a right angle with the radius. And that's exactly what happened in this problem. And so not only did we have a triangle, we had a right triangle. And because we had a right triangle, we were able to do a squared plus b squared equals c squared to find our missing side length. And so that's what we're going to continue to do in all of these problems. And so let's go ahead. Now, moving to B. In this problem, we are just going to assume that this whole side length is just x. Obviously, it's not a great picture here. It makes it look like just part of that length is x. We're just going to call the entire thing x. And so here's what we got. It's a similar problem as before. We have a tangent line, which is 8, because it just hits the circle at one time. And we have a radius that connects to that same point. And because 8 is a tangent line, the radius and that tangent line make a right angle. And so we can solve for x by doing a squared plus b squared equals c squared. So across from our 90-degree angle is our c. So x will be c this time, which means we would just want to do 4 squared plus 8 squared equals x squared in this problem. And so 4 squared is 16, 8 squared is 64, and that equals x squared. Add those two numbers together and we get 80 equals x squared. And then as always, we take the square root as the last step, and x is going to be 8.9. Perfect. So we can do that anytime we know that a segment is tangent to a circle, because every time it's tangent to a circle, it creates a right angle, meaning a right triangle. So we can do a squared plus b squared equals c squared. Now, in this next set, they want us to tell whether it's tangent. We don't know it yet. So I can't just put a right angle there. It's more like, is that a right angle? So I put a question mark there. And so what we need to do is we need to figure out if the Pythagorean theorem is working here. We need to figure out, does a squared plus b squared actually equal c squared? And so let's give that a shot here. Notice this, that's 5. The rest of it is 8. So this whole side is 5 plus 8, which is 13. So we need to assign a c value here. Remember, we can't just decide if it's across from the 90-degree angle because we don't know if there's a 90-degree angle yet. But we can assign c because c is always the biggest number. And so if we're working with 5, 12, and 13, 13 has to be c because it's bigger than 5 and 12. And so what we want to do is let's square 13, and let's see how it compares to 5 squared plus 12 squared, right? We're wondering, does c squared actually equal a squared plus b squared? If it does, then this will be a tangent line. AB will be a tangent line, because if it does actually equal a squared plus b squared equals c squared, that means that this has to be a right triangle, meaning this is a right angle. But if it does not, then it's not a right triangle, and so then AB would not be tangent. So let's figure this out. 13 squared is 169. 5 squared is 25. 12 squared is 144. So let's add 25 and 144 together. The left side's still 169, and 25 plus 144 is actually 169. So obviously 169 equals 169. And what this means then is that the radius and our tangent line are actually perpendicular. They are perpendicular. And because they're perpendicular, we know it had to be a tangent. So we know, yes, AB is a tangent line. Now, let's keep going. All right, so next problem. We need to look at this triangle. We need to call one of these C. Obviously, 20 is the biggest number here, and 20 spans that entire length, so we didn't have to chop it up or anything like that. And so we need to see, does 20 squared actually equal 8 squared plus 16 squared? So 20 squared is 400, 8 squared is 64, and 16 squared is 256. So if we add those two together, we'll get 400 on the left, but on the right, we get 320. That's way less than 400. So obviously these do not equal. And when they do not equal, that means it's not a right triangle, so it cannot be tangent. So when they do not equal, we can say AB was not tangent. All right. Now, one more time, the reason why we can say that is because if a squared plus b squared equals c squared actually works, that forces it to be a right triangle. And when it's a right triangle, it is a tangent line. But if that does not work, then it's not a right triangle. And so if a right angle is not created at the tangent line in the radius, then it's not really a tangent line. And because a squared plus b squared equals c squared did not work in this problem, we were able to say not a tangent. So let's try one more. Decide which letter or which value is C. 25 is the biggest, so that'll be C. So let's compare 25 squared to 7 squared plus 24 squared. We're going to do this a little bit quicker this time. On the left, 25 squared is 625. If we just do this whole calculation on the right, 7 squared plus 24 squared, we will get 625, which is great. 625 equals 625. So because it works, we know AB is actually a tangent. All right, next theorem. So if two segments from the same exterior point are tangent to a circle, then they are congruent. And remember, congruent has a symbol. It's the equal sign with the squiggly. And remember, it essentially just means equal. So congruent and equal are pretty much the same thing. And so here's what this picture means. If two segments from the same exterior point, exterior means on the outside. So I'm going to put a point out here. I'm going to call it point S. And then I'm going to draw point S to be a tangent line over here. Remember, tangent just hits a circle once. And then I'm going to draw another point S to be a tangent line on the other side of the circle. And we're going to call those new points R and T. And basically all it's saying is, if we have these two lines, so RS is one line and ST is the other, so if we have those two lines, if they are tangent, then RS equals ST. So if they actually are tangent, then they equal each other. So I'll put those congruent tick marks through. And so let's just see how this works. So in the next set of problems, example A, it tells us AB and AD are tangent. So we know they're tangent. So this line is AB, the 12. The other line is AD. We know they're both tangent because they're tangent. They have to equal. So all we want to do is do 3x squared equals 12. And we just solve for x. So divide by 3. X squared equals 4. We don't want x squared, we want x, so we square root it, and we just get x equals 2. Perfect. So again, all we're doing here is if we know both lines are tangent and they come from an exterior point, so like point A on the outside of the circle, if they're both tangent, then they equal each other. So now 7x minus 2 is going to equal 3x plus 8. Subtract 3x from both sides. We get 4x minus 2 equals 8. Add 2 to both sides. We get 4x equals 10. And then we divide by 4. And x equals 2.5. Perfect. So one more example. Remember, if these two lines come from the same outside of the circle point, we call it an exterior point, and they are both tangent, just like the example says, they are both tangent, then they just equal each other. So on this one, x squared plus 25 equals 50. Subtract 25 from both sides. We get x squared equals 25, and then we square root both sides, and x equals 5. Perfect. So two tangent lines coming from the same point, set them equal to each other, solved in a variable. All right, last thing for the day, let's just review the new words we've learned, and we're just going to match them to what we see in this diagram. And so let's just go 1 through 8. So point of tangency. Remember, that's just where a tangent line hits the edge of the circle. And so there's lots of them. It could be D here. It could be C. It could be E. And it could be H, right? There's 4 different tangent points of tangency here. So let's look at our options. Which one of those do we see? So D, C, E, and H. Letter E, we see C. So we're going to put C here. That is our point of tangency. We'll cross that off. Now, center. Center just means center of the circle. So that's A or B. Which one do we have? There's B. So we'll put letter H by 2, and that's good. Now, I'm going to start clearing up my circle a little bit just to give us fresh picture each time. For diameter, remember diameter is just a line that goes all the way across the circle. In the circle on the left, we don't have a line that does that. But on the circle on the right, that would be HF. And when I say it goes all the way across the circle, remember a diameter goes across the circle through the center. And so the only one that is in existence here is HF. And so let's look for an HF, and there it is, letter C. Ooh, I see, I made a mistake. This first C I wrote letter C because it was letter C here, but it really should have been option E. Don't put an E there. All right, now back to the diameter. Diameter was letter C, and so now I'll cross off letter C. Remember, that was really segment HF. All right, now a chord. A chord is a line that has endpoints on the circle. It's a segment that has endpoints on the circle, so no arrows. And so I'm going to clean up this right side. Let's look at our options, and here's our possibilities. It could possibly be AD. Remember, no arrows. Could possibly be DG. No arrows. So those are only 2 options, so let's look at those things. AD. Now, remember, a chord has to have an endpoint on this edge of the circle. It has to have 2 endpoints on the edge of the circle. A is not on the edge. It's the middle. So it can't be AD. So let's look then at, so it can't be AD. So let's look then at DG. So here's D to G. And if we don't put the arrows, it just starts and stops at DG. And that's exactly what a chord is. So write letter F here. No arrows, it just starts and stops on the edges of the circle. And so that's a chord. Now, a secant is the same thing as a chord basically, but it continues forever. So this time it does have arrows. And so I want you to see letter D here. See how letter D is DG as well, but the one we just answered had DG with no arrows on the top, and this DG has arrows on the top. That's the difference between a chord and a secant. And so for number 5, our secant is letter D, because if you follow DG, but you extend with arrows, that turns it into a secant. All right, 3 more. So let's cross off D, and let's clean up this side again and the circle a little bit. So common internal tangent. So remember, that's a tangent line. Hits common means it's going to hit both circles in one spot, but it goes through the center. And so that's this line right here because it's crossing in between our 2 circles. And so that line would be CH. So let's look for a CH. It does have arrows on the end, so that's option A. So we'll put A here. Now, for external tangent, remember it's the same thing. It hits both circles in one spot, but it does not go in between. It stays on the outside. So that would be this line right here, DE, with arrows on the end. And so that's letter G here. And then finally, a radius is just a line from the center of the circle to the edge of the circle. Process of elimination tells us that that's B. And so we can fill that in, and here's why. From A to D, right? A is the center, D is on the edge. That is what a radius looks like. So awesome, we made it through part 1 of Unit 7. Got a lot of new information about circles, particularly vocab. So go ahead and try the part 1 worksheet. Work through all those problems. Please email me if you have any questions, and let's keep moving forward. Thank you very much.